Well, in general, I would say math and science is the hardest to teach Socratically in a certain sense because you've got so much content you have to cover. That said, at St. John's, where I attended as an undergraduate, 4-year Great Books curriculum, we had 4 years of math and science all taught Socratically. So there we're doing the great classic texts in each of the subjects. And actually to do a first thing on geometry, and I don't know, probably not something you could do right away, but we used actually Euclid's Elements to do geometry, and we studied Euclid's Elements. And I absolutely loved it. Have either of you by any chance actually looked at Euclid's original Elements?
I'm actually offering it as the honors option.
You are! You are!
It's not the pure
right.
form. I'm doing a web-based one where they already have the figures drawn out for them. So
yes.
It's a little easier for the high schoolers to get.
Fantastic.
Nobody's taken me up on it yet, but they have the whole year to work through it. So
and how did you get into that?
We're required to offer honors, and I went to University of Dallas. So
okay, excellent.
Similar kind of great books education.
Did they do Euclid there?
No, but I knew a lot of people who talked about it.
Okay, okay.
So I'd already heard of it coming into the school.
Okay, that's fantastic. Have you ever had any exposure to Euclid?
I know of it, and it's been described to me, but I haven't gone beyond that.
Yeah. One of the things I loved about it is the way we did it at St. John's. It starts with the common definitions and common notions and so forth. And we will spend a lot of time discussing, kind of abstractly. A point is that which has no part. And exactly what does that mean? So kind of philosophical and non-mathematical, not what standard math is. But then one gets into the propositions themselves, and the way we did it was thinking and asking questions about each step in the process, and asking why did Euclid include this step in the process? What is he trying to do there? And has this been proven or not, or how do we know it's been proven? And by means of doing that, proposition by proposition, I would say that one develops a much better sense of mathematical proof than in a standard geometry course. My sense is that a lot of students, when they take high school geometry, a lot of the two-column proofs are not very rigorous or compelling.
Yeah, and they have a really hard time.
Yeah.
Really hard time putting a proof together.
Yeah. And I think some of it is, I think proof's hard. Just when I've done Euclid, there's some students with mathematical minds who get it immediately. They just whoomp. And there are others where I would say, I did a mixed ability high school geometry class at my last high school using Euclid, and there were 1 or 2 students who got the game of proof, so to speak, on the first week. Others it took at least a semester, and it was one by one. But a lot of it is really spending time thinking and arguing about the steps and how do we know. And for me, I think mathematically and logically, and so I love the kind of coercive power of proof. It just feels good. But I think for a lot of students, it can take a lot of time, and it helps to argue in that case because they can hear others articulate. And some contemporary mathematicians are sometimes critical of Euclid because not all of the proofs are completely rigorous. But actually, an advantage of that pedagogically is when he uses a move that would be considered illegitimate in modern mathematical proof, often students get that. There's one proof where he superimposes one triangle on top of another as grounds for an argument, and that's not considered adequate in modern mathematics. And students often say, well, this doesn't feel right. It doesn't feel like the other proofs. And so by means of, in some ways, endless arguments as to what constitute a valid and legitimate step in a proof, as well as just the practice of memorizing. So one of the things we do at St. John's is you memorize proofs, and students are one by one responsible for doing a proof on the board. And when you get into the longer ones, it's quite a lot of work. So they both memorize them and do it on board, but then they argue step by step what's legitimate, can we skip it? The other thing is, can we skip it? Are there superfluous steps in proofs? But doing this, I would say, gives students a much better understanding of mathematical proof than standard geometry courses. I did Euclidean geometry at San Antonio Academy, a military school in San Antonio, and years later, one of the students came back and he said he'd majored in math at the Naval Academy. He said that one semester of Euclid, he learned more math than all of the other math courses he'd ever taken in his life, just because you spend a lot of time going deep into the guts of it. So even though your students haven't taken you up on that, if you can get a small cohort. The other thing is, I think once they get into it, they'll enjoy it more. Just precisely because I love real proof. That's why I hate standard high school geometry textbooks. You look at those and it's just so artificial. So if you can, I think that would be, I know Timothy Hall has a real commitment to the Socratic method here, and then Melissa is also very supportive at Thales. And then there's kind of a classical education strand, and so I think it would be really interesting to kind of have Euclidean geometry in all of this. Outside of things like Euclidean geometry, which is ideal, at St. John's we go through Ptolemy, Copernicus, Kepler, which is an extremely long, I found it fascinating to experience the Copernican revolution from the inside, but nobody else is going to do that. That's pretty esoteric and out there. So beyond that, in terms of math and science seminars, I think of it as conceptual teaching. So in standard math courses, I've done seminars on, for younger children, the concept of infinity. Even third grade, is there a last number? Is there not a last number? For older students, things like functions and variables, because sometimes students think of, just, okay, we have letters instead of numbers, and we're learning how to solve this, but the relationship of a variable within a function is a concept. And so I've had, once a semester, when you're getting students to a certain level, let's think and talk about what's going on in a function and with a variable and so forth, and then multiple variables. So there, a lot of times whether it's social studies or English or math or history, whatever, I encourage people to look at their curricula in terms of concepts. So in, say, middle school physics, a lot of times students can memorize F equals ma, and they can do various problem sets based on F equals ma, but they don't really understand it. And so sometimes we'll have conversations where I'll use a definition, and again, what is actually going on in this equation, and get them to think and talk about it so that it's internalized in their own words, in their own language. And so in many cases, if you look at your curriculum and you think that there's certain places where there are really important concepts, and by means of lecturing and or doing problem sets, the students aren't really getting the concepts, then it might be worth identifying a text. Sometimes it's a definition or an explanation, and just having a conversation about it. And part of that is you have an exposure to the way their minds are thinking. And sometimes it seems so obvious to you. You get them thinking and talking about it, and you think, okay, we got a long ways to go. And so then you can coach them on understanding the words on the page in terms of developing an understanding of the text. And then at the end of it, if they don't quite get it, then you can clean up with a little mini lecture that helps them get it. In addition to conceptual teaching using Socratic method, you can also obviously look at controversial sorts of things. There are all sorts of science and public policy sorts of issues. I'm in some ways less enthusiastic about that, just because people sometimes just get arguing about political things rather than really get into the science and thinking. My ideal text in many ways is to get students to think fresh and in new ways. The other thing in between sort of pure concept teaching and kind of public policy debates might be interesting frontiers of science, because in real science people are always discovering new things, and there's a lot of uncertainty at the frontiers, whereas in textbook science, I don't know if you have read Thomas Kuhn's The Structure of Scientific Revolutions, but in textbook science it's all 100% known, and I always like to expose them to a hypothesis where there's a little bit of uncertainty.
Sure. And I talk quite a bit about the scientific method and that, how do we build this body of scientific knowledge? Try and ask some questions about how would you build an experiment to test this hypothesis. In fact, my idea for laboratories now is to try and set them up as basically those kind of questions. Instead of saying, we're going to do this procedure to measure this thing. Here's a hypothesis. Let me suggest that you need to make a few of these kind of measurements, but you build me an argument to falsify or agree with my hypothesis.
Yeah.
As I see that as kind of a Socratic.
No, absolutely. And again, that's more like real science.
Right.
I actually hated high school labs in science
Right.
because it was perfectly transparent what they wanted me to do. So I remember, boiling water and putting it in a thermometer and pretending that I'd do my lab write-up while I was supposed to be doing the experiment, because I knew, okay, this is what it's supposed to be.
Right.
And that's very different from what real experiments are.
Sure. Because the valid criticism is it can just be a rote cookbook
Yeah.
thing, and then you've taken away all the real thinking that is supposed to be involved there.
And I think part of this is both setting up experiments like that and then getting them to take this seriously, that there are frontiers, and to some extent I think if they all think it's the super collider and you have to have billions of dollars, then it's not very interesting. But fields like materials science, huge exploding fields where how do you know what properties a new material will have, does have, could have,
Right.
And for that, you absolutely need to test, and you have to have a hypotheses, and you have to have hypotheses about if you change this, then what might be the outcome.
Right. And I think the kids realize it's much more interesting to do the work that way, in a Socratic way,
Yeah.
than if I just tell them what to do.
Yeah. Well, and then the other thing is the notion of scientific rigor. I mean, that's why I love Euclidean proof, because mathematical proof is rigorous. And I think sometimes when they see that, every day there are all these articles coming out that studies show, broccoli this, peanuts that, and a lot of it is suspect, I would say. And so the other thing is, how would you develop rigorous studies for this, and what counts? And I think there is legitimate. Math is most rigorous, physics, chemistry, and biology, and you get down to social sciences and lots of muddiness.
Right. As far as empirical knowledge goes.
Yeah.
And it's the harder part is the actual implementation of things. To give grades and stuff. So what I'm thinking is I'm going to try and grade more on the quality of their argument, sort of thing, and
Absolutely. I mean, just, if you look at AP, have either of you taught AP biology?
I haven't taught that. I've taught AP physics, so I'm kind of familiar with that pretty closely.
But AP biology actually has significant essay writing, and the essays are, in a way, applying core biological concepts to real-world phenomena. But it's basically argument. Obviously you have to have your scientific facts correct, but a lot of it is, can you use this framework of certain ideas? So there are certain knowledge of how an ecosystem works that you need to know. They could say, you had this change in the ecosystem, what is likely to happen? And they evaluate it much more on the quality of the argument. And really quality of the writing, and quality of the argument and quality of writing are close. But similar with lab reports, if you have certain evidence, then how you support it. This is again where I see mathematical proof as a necessary prerequisite for writing a rigorous essay, because with a rigorous essay, you have a thesis, and then there needs to be actual, when you say supporting paragraph needs to be valid logical inferences.
Yeah, absolutely. And like as I teach them F equals MA and stuff like that, and I ask them questions and stuff, and similarly to a proof is to get them to approach the problem in the correct, or in the correct order, I guess. Get their thinking in the correct order, what implies what, and not the reverse.
My understanding is there is a logic curriculum at some of the schools.
Well, we're STMA, so we're we're private Catholic school, so we.
But similar curriculum, isn't it?
Similar curriculum. We're a classical curriculum. We have a little bit more freedom in how we teach our classes, because we're not doing AP stuff anymore directly, so we can kind of go with our curriculum as we want to. But a lot of similarity. Very much.
But so the students do learn logic and basic syllogisms and so forth?
Class, absolutely.
Yeah.
No geometry, you guys do.
I have trying to stress, how do we know this is the next step?
Yeah.
Can we
Right.
conclude this from what we
Yeah.
Yeah, and
cited
in my science
before?
classes,
Mhm.
I try and say, okay, if this is the law, what
Mhm.
does that imply?
Yeah.
If this is the situation and this is the laws,
Mhm.
what conclusions can you draw?
Would you say that your students are typically pretty rigorous logical thinkers by the time you get there, or you're really, yeah,
No, not at all.
yeah.
I feel like, I'm sure for you,
My
they,
advanced students.
yeah,
get
there's
it
some
up.
of them that
Mhm.
are getting there,
Mhm.
but on the whole, they have a hard time
Mhm.
seeing how to go from some initial givens
Mhm.
and a law,
Mhm.
and what's the conclusion.
Mm-hmm. And do you have the, because the other thing is grading arguments based on the quality of the reasoning is time consuming.
It is.
So, on the one hand you have to teach it and then you have to grade it.
Yeah,
It's of
absolutely.
course much simpler just to give multiple choice tests. But the ideal, I think, is to have a great logic course, great logic in geometry, so they really get a rigorous sense of that. And then when you're doing the scientific reasoning, also both teach it and then evaluate them on it in a rigorous way and give them lots of feedback. And some of this are examples too, show them exemplary scientific arguments, then show them cases of failure, logical failure. One of the things I do in the Socratic discussions is, a lot of it is real time. The kids are talking from their perspective, blah, 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 blah. But a lot of times I'll try to get them to be much more focused. So, Olivia said this, Randy said this, are you agreeing or are you disagreeing? It's really basic, but that forces them to come out of their bubble and compare. And a lot of times when I'm in a Socratic, I'll use a whiteboard and create definite propositions out of what they said. I think in terms of propositional content. Again, just by nature, fairly logical thinker. And so that way, it's just not their opinion, because their perception is, oh, I get to talk, I have an opinion. You can say, okay, Olivia's said this, and this is the proposition, you said that, and what's the logical relationship? Are they the same or not? And what evidence would count in support of Olivia's proposition? What evidence would count in support of Randy's proposition? And that way, they're connecting their own ideas too. And you could do this with a lab too. You could try to, this is what you're claiming, this is what you're claiming. How do we know if this evidence, and it's a little bit like what I was saying with Euclid, where we're arguing over, is this supported or not? You want to have them competing to see, is this what counts as support, what counts as valid inference? And both, sometimes there are, of course, rigorous syllogisms where there's no ambiguity, but a lot of times there is ambiguity. Depends on exactly how we define this concept, or whether or not we doubt that particular piece of evidence, or whether we have this additional inference that you believe but I don't believe. So it's also helpful to show them that in one sense logic is rigorous and clear, but in the practical application of most arguments, there are all these auxiliary hypotheses and so forth. And so that's part of what they have to learn is it can be made more rigorous, or it would be rigorous if we had X. And I would say it's endless modeling, in real time, talking using your ideas, famous scientists, their ideas, critiquing arguments. In a way, it becomes more like essay writing. A good English teacher will show a thesis on how a well-structured essay is formed and critiquing essays over and over again. You can do the same thing with rigorous scientific argument, rigorous lab report. But they don't learn it quickly. You just
Right.
have to.
No,
it's a long process.
because
Yeah.
it's something complicated. It's complicated.
Yeah.
It's a high level thinking skill, and you don't build it overnight.
One of, if you wanted, and I don't know how packed your curriculum is, but I remember one of the things I loved most at St. John's was, I believe it's an 18th century, either 17th or 18th century piece by, I think, William Black was the name. He was friends with the guy who did James Watt. And he developed the concept of specific heat. And one of the things that's interesting about this argument is, there's temperature and then there's heat, and then, what's going on there exactly? And so we had to develop a new concept in order to make sense of how temperature changes, not just with respect to ambient temperature, but also what's going on with these solid objects. And it's interesting to see what happens when you have to create a whole new concept. It's a very rigorous kind of argument where just our intuitive notion of heat is not adequate. Our intuitive notion of temperature is not adequate. We have to have a whole new concept in order to make sense of this. And it's fairly accessible. And so there are a few pieces.
Yeah, I'd like to.
Yeah.
That could definitely be like an honors thing or an extra.
Yeah.
Sorry, it's a book or?
It's a paper written, 18th century, and for a capable reader, it shouldn't be too hard. But I think examples of rigorous scientific reasoning like that by famous scientists are useful that are reasonably accessible. And so we can look for a couple of pieces like that. If you don't, so you don't use AP at all anymore?
Yeah, we don't. We're just, we do our own curriculum.
Are you the bulk of the math science department?
There's two more. There's one more chemistry, biology teacher, one more math person, and so there's four of us.
Well, we've been talking about, the problems with, say, AP American history and so forth, but in the sciences, what are you doing instead, or what are your criteria for math and science at that level? Because there's just so much you could cover.
Yeah, there is. I mean, I think it's kind of a great thing for me. I have maybe a list of 10 things that I know, we need to do Newton's laws, we need to do motion, we have to do momentum and collisions, heat, some thermodynamics, and electricity and magnetism. I sort of have those general things in mind, but I don't have much more than that as far as I have to do this or I have to do that.
And is the goal to just give them is it college prep? Is that the primary goal?
College prep.
Yeah.
And so, I guess my primary thing is to make sure, to give them as many chances as I can to think the way I want them to think. Right? Given this, given these laws are here, can you put together the facts? Can you solve a problem? And as long as you can do that, I'm happy.
Yeah. And would you say you dumped the AP Physics exam because it was just too content dense and you want to focus more on thinking?
No, I guess I wouldn't say. Our kids can take the exam.
Right.
They can pay and take the exam. But if they want to pass the exam with a 5, there's probably some extra stuff they're going to have to do to
prepare.
I won't get to. So and we dumped it just because we felt like we just couldn't make it work. Wanted to have emphasis on the thinking skills primarily instead of knowing
tons of stuff. Right.
I mean, like on the AP Physics exam, they get into what we would call very basic quantum mechanics, and I just won't get there. But if I can teach them during the course of the year how to think, well, I can point to them. Okay, go read this. I've got plenty of college physics textbooks. Go take this home and read this, and you should get it. And we can talk about it after class, after school sometimes. But so we'll see how that plays out.
And do you create your own problem sets?
I have a textbook, so I have the Conceptual Physics, which is a pretty widely used textbook. But I do write a lot of my own problems. And, the reality is I don't really do that many. I don't ask them to go home and do all that many problems, to be honest with you. They have to do some lab reports. They have to do some problems, but not many. That I mostly pick out of the textbook in the interest of, because I don't have time to write much problems.
Would you say you're trying to get them to have kind of a more intuitively solid understanding of
that's
physics?
What I'm after. I guess I'm going a bit of a different direction.
Howard Gardner has one of his early books, I think it's called Understanding Minds or something like that, but he tells an interesting story of even graduates from Harvard who of course in physics have gotten good grades can't really understand a simple physics problem like what happens when you throw a ball up in the air and come down.
I've seen
yeah.
right,
Yeah.
and they don't.
They become proficient at doing what it takes to do well on problem sets, but they don't really understand what's going on with respect to physics.
Right. And so, I mean, this is kind of idealistic, and but I think it's the right thing to do.
Oh, I absolutely agree.
I'm sure you do too.
Absolutely agree. And yeah, at St. John's, one of the big criticisms is we don't cover enough. So
Right.
if you want to go off and get a graduate degree in math, science, or engineering, then you have to take another year or even two of standard courses and a lot of it's problem solving. You just don't have the experience doing standard problem sets. And in most graduate courses, lots and lots of problem sets. On the other hand, you do spend a lot more time understanding, and understanding is slow. You kind of have to think, and you have to try it on, and you have to kind of align your understanding of the world with, whatever the concepts are.
Yeah. Yeah, I mean, going through as a, in a traditional kind of curriculum, but one of the, I would say my physics didn't really set in until, as a first-year graduate student, I had to sit through general physics again, and then I would say, okay, now I'm really putting things together.
Yeah.
And it just takes that much time.
It does take time. The other thing we do at St. John's are a lot of very basic pendulum experiments and inclined plane experiments, kind of Galileo 101, and read a lot of Galileo. And in a way, it's really simple, but in another way, to align kind of one's intuitions with the equations, with the concepts.
It's powerful.
It is powerful. It is powerful.
It's powerful in the sense that it's the best thinking.
Right. Right.
You're not just trying to put numbers into formulas.
I suspect you would enjoy a lot of the St. John's math and science curriculum.
Yeah. I suppose, is it out there?
Yeah, it is out there. I mean, again, I think, Ptolemy, Copernicus, and Kepler is just an insane sequence to do.
I did
but
an astronomy elective, and we
Right.
spent half the semester, I would say half the semester, thinking about the ancient astronomy, why.
Yeah.
It was kind of a history and astronomy.
Yeah,
we
yeah.
talked about. And again, it was really, and of course, since we're a Catholic school, we talked a lot about how the church plays in with
Of course.
Galileo.
Just if you have an advanced course or an elective, one of the things we did at St. John's our senior year is Einstein's 1905 paper on special relativity. And it turns out that that's relatively accessible. It's hard and a lot of work, but I think
The mathematics is not that.
Exactly.
There's no differential equations in it. It's just
Mostly algebra,
Yeah.
but it really is. For one, it's an example of amazing conceptual thought. You just sort of see, inexorably, with these assumptions, this logic leads to this conclusion. Out pops E equals mc squared at the end.
Right.
And all the weird implications.
I would like to see the St. John's
Yes.
curriculum, and I don't know if you point me to
Yeah, if you
where
can't find it
can-
online,
just
you can email me and I'll see if I can,
Okay.
show you.
It's the college's curriculum you're talking about?
Yeah, St. John's College
Okay.
math science curriculum.
All right.
Separate from that, just something I do that's fun, that's much, much easier is, do you know Flatland?
I think I've heard that, but I
Yeah.
don't
I have
know.
friends who have read it, but I haven't.
It's fun. It's a 19th century, written in the 19th century. It's a kind of fantasy science fiction story of a two-dimensional world, and then a sphere passes through the two-dimensional world. And the people in the two-dimensional world don't believe that the third dimension is possible. And so it's kind of fun speculation, but they also have to, conceptualize if this is 2 to 3, then what might 3 to 4 be, and that kind of sort of thing.
That's from the 19th,
19th century. Actually, there's another collection called The World of Mathematics that was, I think, compiled in the 1940s, and it's a 4-volume set of mostly essays on math, but also science, but a lot of great scientists. And just in terms of resources of marvelous pieces for your students to read, I would highly recommend it. I think Edwin Newman is the editor. But for instance, they have Haldane's on being the right size, going through why animals are a certain size, and at some point, to read the original arguments for things like that, allow them to apply basic mathematical reasoning to fascinating things. So the world of mathematics, I'm pretty certain Newman is the editor. And just those 4 volumes will have more than you can possibly cover. And it includes some of the material on the St. John's curriculum, some classic texts. So it's just fun to have those sorts of resources. So even if you're, marching through this, I didn't realize just how much freedom you guys had to do marvelous things.
Yeah, we have a great. We do have a lot of freedom.
Yeah.
I mean.
More so in sciences than math.
Yeah,
because they still have
that's
to do
true.
SAT type.
Right.
That's true.
Although even with the SAT, you need a certain fluency in algebra and a certain amount of geometry, but you don't need that much mathematics to do well on the SAT. And so if the SAT is the only math target, reasonably bright students have some freedom to go above and beyond.
Yeah, absolutely.
Well, I need to give another talk, but great to meet you. And
thanks, Rick.
feel free to be in touch. You can get my email contact from Timothy C. Hall.
Okay.
Okay, thanks.
Mike.
Yep.
Thank you.